Hello, my name is Nicholas Stewart, and this is my demo video for Experiment 7. First, I'm going to connect my power to the breadboard. So I'll connect one end of the wire to 5 volts and connect the other end of the wire to the plus sign on the breadboard. Next, I'm going to connect my ground to the breadboard. So I insert my wire into the hole here and make sure that the metal is touching the metal. Oops. Then I tighten it. This is kind of hard to do with one hand, so I'm going to do this really quickly. Okay, then I'm going to place the other end into the minus sign on the breadboard. There we go. Now I have my power and my ground connected to the breadboard. Next, I'm going to place my chips onto the breadboard. The circuit that we're trying to construct is this circuit here, figure 7-1. For this circuit, I will require a XOR gate, 2 NAND gates, 2 inverters or NOT gates, and 1 OR gate. First, I'll place the chip that contains the XOR gates. That is chip 7486IC. I will place that in the center of the breadboard. Next, I'll place the chip that contains the NAND gates. Chip 7400IC. I'll place that here next to the chip that contains the XOR gates. Next, I need to place the NOT gate chip, 7404IC. And finally, I need to place the OR chip, 7432IC. My chips are now placed on the breadboard. Next, I need to form the connections between the chips. The XOR gate is connected to both NAND gates. So it looks like I should do the NAND gate connections first. The first NAND gate has its first input connected to the first input of the XOR gate. So the first input of the XOR gate is pin number 1 of the XOR chip. So I'll place one end of the wire into pin number 1 of the XOR chip. And the other end of the wire needs to go to the first input of the first NAND gate. That's pin number 1 of the NAND gate chip. That's right here. Next, I need to connect pin number 3 of the XOR gate to pin number 2 of the XOR gate chip to pin number 2 of the NAND gate chip. So 3 to 2. Let's connect pin number 3 to pin number 2. Hold on. Sorry. There we go. Pin number 3 is connected to pin number 2 of the NAND gate chip. Next, pin number 2 of the NAND gate chip must also be connected to pin number 3 of the to pin number 4 of the NAND gate chip, because pin number 4 is input 1 of the second NAND gate. So we need to connect 2 to 4. There's another space for 2 right below this space here. Right below this space here, there's another space, so I connect that there. Oh, let me use a smaller one, a smaller wire. I don't need a large wire for this. There we go. I connect this end of the wire to pin number 2, this end of the wire to pin number 4. Oh, I'm sorry. I forgot one of the most important steps. I have to connect each of my chips to power and to to power and to ground. So pin number 14 of every chip is going to be connected to power, and pin number 7 of every chip is going to be connected to ground. Let me check the diagram just to be sure. Yes, pin number 14 is connected to power, and pin number 7 is connected to ground. For every chip, it works like this. Okay, so let's see here. For the first chip, pin number 14 is going to be connected to power. And pin number 7 is going to be connected to ground. Let me fix this and then I'll get back with you. No, actually, let's keep recording. There we go. That goes to ground. And we do the same thing for this chip. Pin number 14 goes to power. Uh-oh. There we go. And pin number 7 goes to ground. The next chip, pin number 14 goes to power. And pin number 7 goes to ground. That's too far away. There we go. Pin number 14 of the last chip goes to power. And uh-oh. I'm missing another. Oh no, no, I'm not. Here it is. Pin number 7 goes to ground. There we go. Okay, I've connected all my chips to power and to ground. Now let's continue with attaching the circuit components together. Let's continue with combining the chips. So we already formed this pathway here from position 5 to position 13. That was that was pin number 2 of the NAND gate chip to pin number 4 of the NAND gate chip. Now we can move on to this part. Pin number 3 of the NAND gate chip, that's the output of the first NAND gate. The output of the first NAND gate is pin number 3 of the NAND gate chip. So we connect pin number 3 to pin number 1 of the NOT gate chip. Pin number 3 to pin number 1. So we connect pin number 3, that's this pin right here, to pin number 1. Next, we connect pin number 6 to pin number 3. Pin number 6 of the NAND gate chip to pin number 3 of the NOT gate chip. Pin number 6. Let's see. 1, 2, 3, 4, 5, 6. To pin number 3 of the NOT gate chip. There it is. Next, we have formed our connections from the NAND gates to the NOT gates, and now we must form our connections from the NOT gates to the OR gate. So, pin number 2 of the NOT gate chip must go to pin number 1 of the OR gate chip. Pin number 2 to pin number 1. Pin number 2 to pin number 1. Next, we need to connect pin number 4 to pin number 2 of the OR gate chip. Pin number 4 of the NOT gate chip to pin number 2 of the OR gate chip. Pin number 4 to pin number 2. Pin number 4 to pin number 2. Oops, one sec. There we go. Pin number 4 is connected to pin number 2. We've completed the circuit. Next, I need to connect inputs A, B, and C to switch 1, 2, and 3 respectively. So let's connect input A to switch number 1. Input A is pin number 1 of the XOR gate chip. So I'm going to connect pin number 1 of the XOR gate chip to switch number 1. Pin number 1 of the XOR gate chip is going to be connected to switch number 1. Next, I want to connect input B to switch number 2. Input B is pin number 2 of the XOR gate chip. So we connect pin number 2 of the XOR gate chip One sec. This thing's bending all over the place. There we go. I connect pin number 2 of the XOR gate chip to switch number 2. Next, I need to connect input C to switch number 3. Input C is pin number 1, 2, 3, 4, 5. Pin number 5 of the NAND gate chip. One, two, three, four, 5. One sec. Okay, pin number 5 to switch number 3. There we go. Now, we're going to have to troubleshoot our circuit. And the way that we're going to troubleshoot our circuit is by utilizing these test points on the circuit. The test points are going to be tested to ensure that the proper inputs are resulting, the proper outputs are resulting from the given inputs. Let's begin by testing test point 1. Test point 1 is at the output of the XOR gate. Let's see. Let me find out in the book what the characteristic of an XOR gate is. Okay, so with an XOR gate, the circuit produces a high output whenever the two inputs are at opposite levels. So in order to test if the XOR gate is working properly, we're going to have to create a situation which would technically make it produce a high output. So let's look at the XOR gate. Input 1, input 2, and output. So pin 1, pin 2, pin 3. We're going to have to check pin 3, but pins 1 and 2, inputs A and B, are going to have to be at opposite levels. So let's make A high and B low. A high, B, A high, B low. That should produce a high output. We're going to use this multimeter to test whether the output of the XOR gate is high or not. Let me just remove these. Okay, the black one is going to go to ground. I'm just going to sit that in here. And the red one is going to be what I'm actually using to check things. Let me connect my power here. And next, let me turn this on. And okay, let's check pin number 3. Oh, first, I have to turn on my multimeter. That would help. I'll turn it to this 600 DC, direct current. If I see a rise in voltage, I know that it's functioning. There is a rise in voltage. So my XOR gate is functioning properly. As you can see, if I turn A down and B down, they're the same. So the XOR gate does not produce a high output. Now, what if I turn them both to high? Still, it will not produce a high output because the XOR gate only produces a high output when both of its inputs are opposite. When its inputs are opposite, rather. As you can see, it's still 0. Next, we'll go to test point 2. The NAND gate. The NAND gate should only produce a high output when both of its inputs are... Well, let's check. Okay, so the NAND gate produces a high output in all cases except when both of its inputs are high. So let's test to see if the NAND gate is functioning properly. That way we can verify that test point 2 is working. So first, we need to make sure that input 1 of the NAND gate is high. And that means that A should be high. So let me turn switch 1, which is for A, to high. Next, I need to make sure that input 2 of the NAND gate is low, which means that the XOR gate should be producing a low signal. So in order to make the XOR gate produce a low signal, let's look at what the characteristics of the XOR gate are again. The XOR gate, the exclusive OR gate, produces a high output whenever both of its inputs are at opposite levels. So we already have A as high, and we need B as low in order to produce a high output. But we want it to produce a low output, which means that we want A to be high and B to be high. So let's make B high. That's switch 2. We're going to switch it to high. And then let's test to see if the XOR gate is low or not. Let me just prepare my multimeter. Placing one end into ground, and the other end will be used to test to see if the XOR gate is low or not. Okay. Let's see if pin number 3 is producing a low signal. And yes, it is producing a low signal. So that means that input 1 of the NAND gate on top should be high, and input 2 should be low in this situation, which means that the NAND gate should be producing a high output. This means that pin number 3 of the NAND gate chip should be high. Let's turn on our test. Oh, sorry, I forgot to turn this on. Let me test that again. The XOR gate, pin number 3. Yes, it is producing a low output. Now let's check pin number 3 of the NAND gate chip. It is producing a high output. This means that test point 2 is probably functioning correctly. Now, in order to test it more thoroughly, let's produce a scenario in which the NAND gate would be low. We already have input 1 as high, but we need input 2 to be high. This means that we need to switch B to low so that the XOR gate produces a high signal and makes the NAND gate low. So let's turn switch number 2 to low. I'm going to test the XOR gate to make sure that it is producing a high output. And it is. And next I'm going to test the NAND gate to see if it is producing a low output. And it is. Test point 2 is working properly. Now let's look at test point 3. Test point 3 should invert whatever is happening at test point 2. Test point 2 is currently high, right? Let's look and see. Wait, no, test point 2 is currently, let's check again. 4 is the input, 5 is, let's check test point 2. Test point 2 is currently low, and so test point 3 should be high. Let's check test point 3. Pin number 2 of the NOT gate chip is the output of the inverter. It is high. It's doing its job correctly. Let's look at test point 4. Test point 4. Before test point 4, we have a NAND gate, the second NAND gate. So, there is a high signal being produced by the XOR gate. Let me check to make sure. Yes, there is a high signal from the XOR gate. And so, that high signal is going to go over to input 1 of the second NAND gate. And input 2 of the second NAND gate is currently low, but I'm going to switch it. Well, it's currently low, so I'm going to leave it alone and then see if the output of the second NAND gate is high. The output of the second NAND gate is pin number 6 of the NAND gate chip. And it is high. Pin number 6, 1, 2, 3, 4, 5, 6 is high. Okay. Now we need to create a scenario in which the NAND gate would not function. In which the NAND gate would produce a low output. That is when C is high. So let's make C high. And the output is now low. Test point 4 is working properly. Let's look at test point 5. Test point 5 should invert whatever is happening at test point 4, and test point 4 is low. Test point 5 should be high. Let's check. That's pin number 4 of the NOT gate chip. Oh, wait a second. Test point 4 is... yes, low in this situation. So let's check test point 5. It's low. That means that something is wrong with test point 5. So let's look at test point 4, the output of test point 4 again. The output of test point 4, the output of the NAND gate again. The output of the NAND gate should be going to pin number 3 of the NOT gate chip. And that is our problem. It is not going to pin number 3 of the NOT gate chip. So the output of the NAND gate chip my goodness, what is going on here? Let's see. So we have the NAND gate chip, and the first NAND gate should have its first input connected to A. So its first input... oh, hold on. I'm looking at the wrong chip. Okay, let's check the NOT gate chip. So the NAND gate, the second NAND gate, the output for the second NAND gate should be going to pin number 3 of the NOT gate chip. So let's see, 1, 2, 3, 1, 2, 3. It is going to pin number 3. So let me check again to see what's going on. The output of the NAND gate chip, the output of the second NAND gate is going to be tested again. So that's 1, 2, 3, 4, 5, 6. The output of the second NAND gate is actually high. I was testing the wrong chip. The output of the second NAND gate is high. And that means that the inverter should cause this signal to be low. So let's look and see. It is. Now, okay, next I'm going to make the output of the NAND gate, the second NAND gate, low, so that we can see if the inverter is still working properly. In order to do this, C is high, but I need to make test point 1 high as well. So in order to do that, I need A to be high and B to be low, or B to be high and A to be low. So let's see here. A to be high, B to be low. There we go. In this situation, the output of the XOR gate should be low. Let's check. Nope, it's high. Let's find out why. So the circuit produces a high output when two inputs are at opposite levels for the exclusive OR gate. So that means that A and B must be at the same level. So let's switch A and B to the same level. And now the output of the exclusive OR gate is actually low. Okay, now that the output of the exclusive OR gate is low, it's going to carry that low signal One sec. Okay, so the XOR gate is currently producing a low signal, and C is going to be switched to high, which means that the NAND gate is going to produce a high output, the second NAND gate. And it is. And that means that the inverter should change it to a low signal. Let's check pin number 4. Pin number 4 is low. Let's see what happens again when I change C to low. The XOR gate produces a low signal, and the C gate is a low signal, and the second NAND gate is still a high signal, and the output of the inverter is low. So test point 5 is functioning properly. Now let's test test point 6. In order to do that, I have to look at test point 3 and test point 5. Test point 3 is low, and test point 5 is low. This means that the OR gate should produce a low output, because an OR gate produces a high output in all cases except when both of its inputs are low. And it is low. Now let's check to see if when we switch test point 5 to be high, test point 6 is high like it's supposed to be. So let's see here. The XOR gate is currently producing a low signal. Let's make C produce a high signal. This will make the NAND gate produce a high signal. Oh, wait a second, that's not going to do it. Because the NAND gate's going to produce a high signal. We need it to produce a low signal. So let's make So C is high. And the XOR gate is currently low, but we want it to be high. So A and B must be opposite. So let's make A high and B low. A high, B low. That way the XOR gate will produce a high output. And C will produce a high output, which will cause the NAND gate, the second NAND gate, to create a low output. And it is. And this will cause, and then the signal will be inverted to a high signal. And it is. And once that happens, test point 3 will be low and test point 5 will be high. So let's try test point 3 again. Test point 3. Oh, wait a second. Test point 3 is actually high right now, but that's okay. And test point 5 is high, so that means that the output of this, of the OR gate, should be high. Because it's in all cases except when both of its inputs are low that it will produce high. And it does. Test point 6 is working properly, and therefore we can conclude that the entire circuit is working properly. Just to verify this, let's look at these scenarios. If I pick this scenario here, where A is low and B is high and C is high, I should get these outputs. Actually, I'm going to pick an easier one. When A is low, B is low, and C is low, I should get these outputs. A low, B low, C low. Test point 1 should be low. Test point 1 is low. Test point 2 should be high. Test point 2 is high. Test point 3 should be low. Test point 3 is low. Test point 4 should be high. Test point 4 is high. Test point 5 should be low. Test point 5 is low. And test point 6 should be low. Test point 6 is low. This circuit is functioning properly, and that concludes my demo for experiment 7.